Hello friends, in this lecture today we shall be talking about the Coulomb's law and the electrostatic forces between particles. The main objective of discussion would be to apply Coulomb's law to the charged particles to relate their magnitude of the electrostatic force, the charge magnitudes of the particles and the separation between the particles. Identify that Coulomb's law applies only to point-like particles and objects that can be treated as particles. If more than one force acts on a particle, find the net force by adding all the forces as vectors and not scalars. Identify that a shell of uniform charge attracts or repels a charged particle that is outside the shell, as if all the shell's charge were concentrated as a particle at the shell's center. Identify that if a charged particle is located inside a shell of uniform charge, there is no net electrostatic force on the particle from the shell. Identify that if excess charge is put on a spherical conductor, it spreads out uniformly over the external surface area. Identify that if two identical spherical conductors touch or are connected by conducting wire, any excess charge will be shared equally. And finally, identify that a non-conducting object can have any given distribution of charge, including charge at the interior points. Coulomb's law. Before starting to discuss Coulomb's law, we need to keep in mind that its equation works for only charged particles and a few other things that can be treated as particles. For extended objects with charge located in many different places, we need more powerful techniques. So here we consider just charged particles. If two charged particles are brought near each other, they each exert an electrostatic force on the other. The direction of the force vector depends on the signs of the charges. If the particles have the same sign of charge, they repel each other. That means that the force vector on each is directly away from the other particle. If we release the particles, they accelerate away from each other. If instead the particles have opposite signs of charge, they attract each other. That means that the force vector on each is directly towards the other particle. If we release the particles, they accelerate towards each other. The equation for the electrostatic forces acting on the particle is called Coulomb's law, after Charles Augustin de Coulomb, whose experiments in 1785 led him to it. Now we will write the equation in vector form and in terms of the particles shown, where particle 1 has charge q1 and particle 2 has charge q2. These symbols can represent either positive or negative charge. Let's also focus on particle 1 and write the force acting on it in terms of a unit vector r that points along a radial axis extending through the two particles radially away from particle 2. As with other unit vectors, r has a magnitude of exactly 1 and no units. Its purpose is to point like a direction arrow on a street sign. With these decisions, we write the electrostatic forces as vector F is equal to k into q1 q2 divided by r square into unit vector r. Here r is the separation between the particles and k is a positive constant called the electrostatic constant or the Coulomb's constant. Now, let's check the direction of the force on particle 1 as given by equation C1. If Q1 and Q2 have the same sign, then the product Q1 Q2 gives us a positive result. So, equation C1 tells us that the force on particle 1 is in the direction of the unit vector r. That checks because particle 1 is being repelled from particle 2. Next, if Q1 and Q2 have opposite signs, the product Q1 Q2 gives us a negative result. So, now equation C1 tells us that the force on particle 1 is in the direction opposite of unit vector r. That checks because particle 1 is being attracted towards particle 2. Now, we will discuss something that is very curious. The form of equation C1 is the same as that of Newton's equation for the gravitational force between two particles with masses m1 and m2 and the separator r. Here, g is the gravitational constant. Although the two types of forces are widely different, both equations describe inverse square laws that involve a product of a property of the interacting particles, the charge in one case and the mass in other. However, the laws differ in that gravitational forces are always attractive, but electrostatic forces may be either attractive or repulsive depending on the signs of the charges. This difference arises from the fact that there is only one type of mass but two types of charges. Unit of charge. The SI unit of charge is the Coulomb. For practical reasons having to do with the accuracy of measurements, the Coulomb unit is derived from the SI unit ampere for electric current I. We shall discuss current in detail in later lectures, but here let's just note that current I is the rate at which charge moves past a point or through a region, that is, I is equal to dq upon dt. Rearranging and replacing the symbols with their units, coulombs, amperes and seconds, we see that 1 C is equal to 1 A into 1 S. Magnitude of force. For historical reasons and because doing so simplifies many other formulas, the electrostatic constant K in equation C1 is often written as 1 upon 4 pi epsilon 0. Then the magnitude of the electrostatic force in Coulomb's law becomes F is equal to 1 upon 4 pi epsilon 0 into Q1 Q2 divided by R square. The constant in the equation has a value of K is equal to 8.99 into 10 raised power 9 Newton meter square per Coulomb square. The quantity epsilon 0, called the permittivity constant, sometimes appears separately in equations and is equal to 8.85 into 10 raised power minus 12 Coulomb square per Newton meter square. Multiple forces. As with all forces, we have been discussing the electrostatic force obeys the principle of superposition. Suppose we have n charged particles near a chosen particle called particle 1, then the net force on particle 1 is given by the vector sum of all forces by this equation. Here F14, for example, is the force on particle 1 due to the presence of particle 4. This equation is the key to many of the homework problems. So let's state it in words. If you want to know the net force acting on a chosen charged particle that is surrounded by other charged particles, first clearly identify that chosen particle and then find the force on it due to each of the other particles. Draw those force vectors in a free body diagram of the chosen particle with the tails anchored on the particle. It may sound trivial, but failing to do so easily leads to errors. Then add all those forces as vectors and not as scalars. The result is the net force or the resultant force acting on the particle. Shell theories for electrostatic force. Shell theory 1. A charged particle outside a shell with charge uniformly distributed on its surface is attracted or repelled as if the shell's charge were concentrated as a particle at its center. Shell theory 2. A charged particle inside a shell with charge uniformly distributed on its surface has no net force acting on it due to the shell. In the first theory, we assume that the charge on the shell is much greater than the particle's charge. Thus, the presence of the particle has negligible effect on the distribution of charge on the shell. If excess charge is placed on a spherical shell that is made of conducting material, the excess charge spreads uniformly over the external surface. For example, if we place excess electrons on a spherical metal shell, those electrons repel one another and tend to move apart, spreading over the available surface until they are uniformly distributed. That arrangement maximizes the distance between all pairs of the excess electrons. According to the first shell theorem, the shell then will attract or repel an external charge as if all the excess charge on the shell were concentrated at its center. If we remove negative charge from a spherical metal shell, the resulting positive charge of the shell is also spread uniformly over the surface of the shell. For example, if we remove n electrons, there are then n sites of positive charge that are spread uniformly over the shell. According to the first shell theorem, the shell will again attract or repel an external charge as if all the shell's excess charge were concentrated at its center. Charge is quantized. In the early days, electric charge was thought to be a continuous fluid, an idea that was useful for many purposes. However, we now know that fluids themselves, such as air and water, are not continuous but are made up of atoms and molecules. That is, matter we know is discrete. Experiments show that electrical fluid is also not continuous but is made up of multiples of certain elementary charge. Any positive or negative charge q that can be detected can be written as q is equal to Ne, where n can be plus minus 1, plus minus 2, plus minus 3 and so on. Here E is the elementary charge, has the approximate value of 1.602 into 10 raised per minus 19 Coulomb. The elementary charge E is one of the important constants of nature. The electron and proton both have a charge of magnitude E. You often see phrases such as the charge on a sphere, the amount of charge transferred, and the charge carried by the electron. That suggests that charge is a substance. You should, however, keep in mind what is intended. Particles are the substance and charge happens to be one of their properties, just as mass is. When a physical quantity, such as charge, can have only discrete values rather than any value, we say that the quantity is quantized. It is possible, for example, to find a particle that has no charge at all, or a charge of plus 10 or minus 6 but not a particle with a charge of, say, 3.57 The quantum of charge is small. In an ordinary 100-watt light bulb, for example, about 10 to the power 19 elementary charges enter the bulb every second and just as many leave. However, the graininess of electricity does not show up in such large scale phenomena, that is, the bulb does not flicker with each electron. Charge is conserved. If you rub a glass rod with silk, a positive charge appears on the rod. Measurement shows that a negative charge of equal magnitude appears on the silk. This suggests that rubbing does not create charge but only transfers it from one body to another, upsetting the electrical neutrality of each body during the process. This hypothesis of conservation of charge, first put forward by Benjamin Franklin, has stood up under close examination both for large scale charged bodies and for atoms, nuclei, and elementary particles. No exceptions have ever been found. Thus, we add electric charge to our list of quantities, including energy and both linear momentum and angular momentum that obey a conservation law. Important examples of the conservation of charge occur in the radioactive decay of nuclei, in which a nucleus transforms into a different type of nucleus. For example, a uranium 238 nucleus transforms into a thorium 234 nucleus by emitting an alpha particle. Because that particle has the same makeup as a helium 4 nucleus, it has the symbol for helium. The number used in the name of a nucleus and as a superscript in the symbol for the nucleus is called the mass number and is the total number of protons and neutrons in the nucleus. For example, the total number in uranium is 238. The number of protons in the nucleus is the atomic number Z, which is listed in this partial table. From this list, we find that in the decay, the parent nucleus uranium contains 92 protons, a charge of plus 92 The daughter nucleus thorium contains 90 protons, a charge of 90 and the emitted alpha particle helium contains 2 protons, a charge of plus 2. We see that the total charge is 92 before and after the decay. Thus, charge is conserved. The total number of protons and neutrons is also conserved. 238 before the decay and 234 plus 4 is equal to 238 after the decay. So friends, here we come to the end of this lecture and therefore we sum up. Coulomb's law describes the electrostatic force between two charged particles. If the particles have charges q1 and q2 are separated by distance r and are at rest relative to each other, then the magnitude of the force acting on each due to the other is given by the Coulomb's law. The electrostatic force vector acting on a charged particle due to a second charged particle is either directly towards the second particle or directly away from it, depending on the sign of the charge. The two shell theories for electrostatics are: a charged particle outside a shell with charge uniformly distributed on its surface is attracted or repelled as if the shell's charge were concentrated as a particle at its center. A charged particle inside a shell with a charge uniformly distributed on its surface has no net force acting on it due to the shell. So friends, that is it for today. In the next lecture, we shall be discussing electric fields. Thank you very much.